All right, we can talk about stuff we've got going on. So we'll have a quiz on Friday. There'll be a homework due Wednesday at 7 a.m. Okay, my office hours today are shortened. I apologize for that. Office hours are 1:15 to 2:15 p.m. Sorry, I have a doctor's appointment for that. Remember that I've got office hours on Friday that are the same as those. There's also the help session on Thursday. Okay, and I'll be around tomorrow too if somebody wants to try and make an appointment. I'm giving the Epic, so I'm not sure where the hours are going to end up. But you know, if you need to talk to me, let me know. We can work something out. All right, questions on things we've got going right now? Yeah. There is an Epic tomorrow. Yeah, at noon. Yes, in here. You have a homework due tomorrow. Yes. Okay. Other questions? All right, then we are going to talk about.
Is the Epic going to be in here?
Yes. As far as I know. Okay, so today we're going to be talking about kinetics. And when we talk about kinetics, your book likes to talk about, what is it? They call it reaction rates. I'll probably call it rate of reaction, or I might be able to hold on to reaction rates. But both of those are the same thing. So when we talk about rates of reaction or how fast things happen, this is really important in terms of chemistry. There's a lot of things you can learn about reactions from how fast they react and how their reaction rates change based on when you play around with things like concentrations and such. What we're looking at right here, just to start off and thinking about this at the molecular level, we've got a reaction which is hydrofluoric acid, which is aqueous in this case. Hydrofluoric acid is that fun acid that goes through your skin and dissolves your bones. It also dissolves glass. Lots of fun working with that. It can react with water, and the fluorine can give up a proton, an H+, to make H3O. So let me do it like this. What's going to happen is our fluorine is going to become F-, plus, and it's also aqueous, and then plus, what we'll have is that proton will have moved over to stick to the water, and now we have what we call a hydronium ion. Okay. Cut out there, but not on my screen for once. And so this is the reaction we're looking at here. Here they've drawn the molecules for us. And for these two things to react, for this hydrogen to move from here to there, those two molecules have to collide with one another. Okay. And not only do they need to collide with another like we see here, but they have to collide in the correct orientation for the reaction to happen. So for this reaction, we have them colliding such that the hydrogen ends up, the hydrofluoric acid runs into the water such that with a hydrogen, and the hydrogen can be transferred. Okay, down here, if the fluorine runs into the water and the hydrogen isn't facing the water, then they're just going to bounce off of each other and no reaction is going to happen. So this is the kinetic molecular theory of reactions. You want to think about what's going on with the molecules, okay, in terms of this. But the main takeaway here, I can do this in one sentence, is that for molecules to react, they have to collide in the correct orientation. So that's in there too.
Okay.
We'll get to that.
Okay, sorry.
Not today. All right, so for molecules to react for today, we're just going to think about them. They have to collide in the correct orientation. Okay, so for thinking about that if we want a reaction to go faster, okay, and the converse for these things will be slower, what can we do? So to make a reaction go faster, you need to have more collisions. How can we increase the number of collisions between our molecules?
Increasing temperature.
Okay, so increasing temperature will increase the molecular velocities. And you'll thus have more collisions. Okay, so we're talking about this is like on if you're playing pool on a pool table and you break it and you break really hard. Really hard break is going to cause the balls to run around more, to go around, bounce around more, and they're going to hit each other more. Okay, as opposed to a really soft break where you're going to have less of that. What else can we do?
Concentration.
Yes, increasing the concentration of the molecules in the reaction. Okay, and really it's the reactants. All right, we'll see this in a minute. But increasing the concentration of the molecules will cause them to run into each other more often as well. There's more of them. Okay, think about it being, you're at a party. If it's a crowded party, you're going to bump into people more than if it's a really sparse party and there's lots of space. Okay, it's a COVID party, let's say. Okay, so increasing the concentration of molecules will cause them to run into each other more often. So both of these are going to speed up the rate of reaction. The converse is true as well. If you decrease the concentration, things will run into each other less often. Questions? All right, so mostly when we talk about reactions, we're going to be talking about reactions happening in the gas. Mostly we think about gases. We got these gas molecules bouncing around. Or we're thinking about things in liquid, right? You're in a solution and you've got molecules in solution that can bump into each other because they can move around. Solids don't react so much. So if I take two solids and I stick them next to each other, I might be able to get some reaction right at the surface, but they're not going to react all the way through because the molecules aren't moving around, right? If I've got two solids here, molecule out here and the molecule here, they can't ever get together to have a reaction. That makes sense. All right. Or you could have a solid in a liquid, or you could have a solid in a gas suspended, like you throw it up into the air. And so in regards to solids, when solids react, surface area really matters. All right, the more surface area, the faster the reaction. All right, I've got a couple examples of that, although there's just a tremendous number of examples. But one example is when you eat food, right? Your food goes into your stomach has muscles that'll squeeze in all sorts of different directions to break up that food. And what it's doing is it's breaking up the food into smaller chunks. The smaller the chunks, the more surface area they have, right? You take something that's a big thing and you break it up into a little thing, you get more surface area, and that makes it easier for the acid to react with those in your stomach, and also for, more importantly, the enzymes in your stomach to come in and break that food down. Okay, that's one example. Another example is grain silo explosions. Probably gonna have to watch an ad here. Oh, hold on. I haven't closed this. Forget that one. Let's do this one where we've already.
397
Oh.
Farmers Rice Milling Company. Came on scene, the top of the elevator was smoking, along with.
We don't need the sound. We just want to see the explosion, right? The explosion's over here. Okay, here we go. So, got a grain silo here in the background, and apparently they caught it on film when it went off. Does anybody know why grain silos explode or what causes that? How it's related to the surface area of solids? Essentially, you get a bunch of dust. You throw this grain into the silo, right? It rubs against each other as it goes. It creates this dust, And if you get and so it has a very high surface area, all right? And so what happens is that if you get a spark in there, there's oxygen in there, that can cause it all to go up. It goes up really fast. It can react very fast to the all surface area, if that makes sense. If you were to take, another thing you could do is if you take flour and throw it at a flame, you get a really kind of spectacular sort of burst of flame if you can get it all spread out nicely. Okay, so that's an example of that. And then if you wanted a better, that one we just got to see, we got to see it explode. It blew up the top a little bit. But if you wanted a better example or something where you've got more spectacular sort of things, here's a set of grain cells. We just blew the sides out in terms of that explosion. So that's an example of surface area being important in terms of solids and chemical reactions. Yes?
Is that also true of when things are liquid, like molecule size? Like, isn't if it's larger and has a larger surface area, it has more potential to react?
Not so much.
Not
Okay.
so much.
Yeah. So what you would want is you want a lot of little molecules. So if we're thinking about like proteins or something like that, certainly if we think about individual protein, we have a protein this big and we have a protein this big. The outside of this protein has more surface area to react, but proteins generally only react in certain spots. It'd be better to have a bunch of little proteins for a reaction.
That makes
So if
sense.
you're thinking about, let's say, breaking it down in your stomach. Okay, so we've got those things that affect the rates of reaction. Right, so what we're going to do now is go into some nomenclature. We're going to talk about how to describe reactions and make equations that will help us figure out rates of reaction. Before we do that, what I want to do is look at this figure from your book where they're showing kind of this is a graph that kind of demonstrates this principle of concentration for us actually. So if we have this reaction, this carbon dioxide reacts with chlorine gas to make, I don't know what the formal name of that thing is, or the common name of it is, but we've got, let's make this product. What we have is, so as we see here, you've got a curve describing the rate of reaction here. So this is how much the concentration is increasing with time, all right? And this is how much the concentration of reactants is decreasing with time. And you see, if I was to look at the rate is equal to the tangent, what we would call the instantaneous rate. We'll talk about that in a minute, but is equal to the tangent of the line. So it's the slope. So if I look at the rate right at the beginning of reaction, that's how fast it is. Okay, really steep slope. And if I look at the rate at the end of reaction here, near the end of our monitoring, it's a less steep slope, right? So what's going on is we're making products slower as we go through the reaction. We start out fast, it gets slower. The reason it gets slower is we just talked about how if you decrease the concentration, let's go decrease. If you decrease the concentration of the reactants, the reaction goes slower, right? Well, as this reaction goes, reactants get used up. Because we start out with 1 molar of our reactants or whatever reactant they picked, and the concentration goes down as the reaction occurs, and that slows down the reaction. Okay? We're less likely to have these two things run into each other if there's less of them because they've been used up. That make sense? Okay, so we can actually describe this reaction. I'm going to type this out. So I might say rate of reaction. That's equal to, and your book, rate of, you talked about this, is rate of change of COCl2 is equal to, and now I'm going to finish off the equation without typing. Okay, if I want to describe that it would be the change in COCl2. Please get used to me doing chlorines like this. Okay, I do the little cursive L there at the end. I kind of connect them because I don't want you to think it's a carbon and then an iodine. If I just do a straight up L, but I know some people get confused by it at the beginning, but I feel like it's more clear in terms of drawing things. Over change in time. So we have the change in the concentration of this product over the change in time. How many people have had calculus or are in calculus? Okay, so some of you, if I don't know that your book is ever going to use calculus speak for this, but more formally, if you were doing calculus, this is the way you describe that. Okay, I'm going to stick with whatever your book does. Okay, but that's a way we can describe it. So for unit time, we have a certain change here. And if we look at that reaction, we can think about the unit time matters, right? Okay, the unit time for the change would be, tells us we could have more change per unit time if we have more time, but then we're getting an average of rates. So this figure right here really demonstrates the difference between average rates and instantaneous rates. So if I look at this, this is for, I think, the same reaction. Yeah, it is right there. It's showing us the formation of COCl2. And so the average rate, if we want to go over this 10 seconds here, is going to be that point minus that point, right? Rise over run. Okay? And if we think about it as a slope, that slope represents is going to be what our rate is. It's going to be, the slope is right there. Okay, does that make sense? So we have an average rate, and that's this one. All right. For those of you in calculus, we could take the derivative and we could get the tangent to the line. And that's going to be our instantaneous rate. And so that would be an example of this. And you see how they're different, right? For this point right up here, I could take that as an estimate of what the rate was for this, but I'd be better off getting an instantaneous rate because this is faster than this, right? The slope is more, no change. Concentration over here, so if it was flat, nothing would be happening, right? Nothing would be being made for this fraction. And if I was interested in T1 here, that's a faster rate than the average. Right, so this is a faster rate than that, and that's a slower rate than that. So these instantaneous rates are important. And essentially, to get an instantaneous rate, you would just make your time, you could make your time really small. How much did it change for a really tiny change in time? How much does that change? And I can get that slope. Okay. Questions? Okay, so today's going to be fairly abstract. We're going to get into more or less abstract things at the end and also as we move forward. But kinetics is super important, okay? You can find out all sorts of interesting things using kinetics. My professory research for 2 decades, probably 2 decades, let's say, maybe more than 2 decades, involved kinetics. I was using kinetics to try and figure out how tightly things bound to an enzyme, mostly. Okay. But you can tell so many things. If Dr. Brenzovich still taught chemistry instead of all honors, he uses kinetics a lot. In terms, he'd be teaching organic, but he uses kinetics a lot to figure out what's going on in reactions. Okay, so let's go ahead and we want to think about the difference between instantaneous rates and average rates. Okay, we also want to look at, we want to think about how we can describe how much of a product or reactant we're making. So let's say we're looking at the reaction that, this is one of the reactions that helps send the space shuttle into orbit, right? Hydrogen gas reacts with oxygen gas to make water. It's hot water, so it's going to be water gas. And if we think about this reaction, I have a rate here, so for every oxygen I consume, how many hydrogens do I consume? 2, right? Okay, so if I want to express these equations, if I knew the rate for this and I was trying to figure out the rate for that, right? If this was 1 per second, okay, what's the rate of that going to be? Consumed. This is 1 goes away per second, 2 goes away per second, right? So we can describe these things with an equation. If I want to think about this reaction up here, if I have my change in oxygen concentration per change in time, right? Okay. If I wanted to have, that's going to be equal to, well, first off, what's going on with my oxygen? Is it going away or am I making it? It's going away. So I need to put a negative sign in front of that. All right. That's going to be equal to, if I'm going to talk about my change in concentration of hydrogen per time, right? This goes away twice as fast, right? So if I'm going to make it equal to this, I need to put the 2 on the bottom. All right, that's going to make those equal. And what about on the other side? Am I making water or is it going away? Making, so that's going to be a plus. Change in water over, and then now, once again, how many waters do I make per oxygen? 2. So that's how I can relate all of these rates. Taryn, did you have a question or did I answer it?
You answered.
Okay, great. Does that make sense? So for any equation like that, you're going to take these coefficients and you're going to put them on the bottom versus time. Let's try a problem. Okay, so what I'd like you to do is using that, what I just did, or actually I'll do the first one, but we're going to use that to solve something here. First of all, the overall reaction rate. What they mean by the overall reaction rate is they mean the rate of something that has no coefficient. Okay, so if you had no coefficient, what would be the rate? They don't define that in your book. I'm not going to give you problems with that. I don't like the terminology. Okay, so we're not going to worry about overall reaction rate. We're going to be worried about using the stoichiometry of this reaction to relate how fast we make or use something versus something else as the reaction goes. All right. So what we want here is the rate of change for water. Okay, and we're given, if we look up here, the reaction describes the combustion of dimethyl sulfide. If the rate of production of carbon dioxide is this, find the other things. So we're given this, and we're going to be asked to find that, right? Well, I know that the rate of change for carbon dioxide concentration, and whenever I put those brackets, we mean molar, concentration here over time. What's the coefficient in front of my carbon dioxide? 2. That is going to be equal to the rate of change of water, right? I missed something, by the way. Well, no, I didn't miss something, but I did. We'll talk about it once I get done here. What's the coefficient in front of the water? 3. Okay, those two things are equal to each other. Am I making them or are they getting used up? Making. So we're going to put pluses in front of there. You could just leave it and not put the plus since it's not negative, but let's put the plus just to be really explicit about it. Okay? All right, so I've got an equation here. And my equation is, I've got 1, 2, 3 unknowns, right? Okay? And I'm given one thing up there, right? I'm given what the change in CO2 is, so I can put that in. And then what about the times? I don't know what the times are, do I? How do the times relate to each other, though?
Shouldn't they be equal?
They're the same, right? Whatever time I pick, right? I could pick it as 1 second since this is per second. I can make it 10 seconds. I can make it 100 seconds. I can make it whatever I want. But they're the same, and so what's going to happen with those? They're going to go away. They're both on each side. We've got time on the bottom on both sides of the equation, so I can cancel my times. All right, so if I go ahead and rewrite this with my number, what was it, 0.120? Yep. 0.120 molar per second over 2 is equal to my change in water rate times nothing. So now I just need to solve this, right? I'm going to multiply that times 3. My 3's go away. And so it's going to essentially be times 1.5. Bless you. 0.180. .180 molar per second is equal to my change in water concentration. And really, I don't have it written there, but we canceled the times, but it's really per time, right? Change in time. It's going to be per second. Yes.
So what's the difference? I mean, like, I know that like refills have like extra and stuff like that, but and they always have a constant. But what's the difference between doing this and doing a rate law?
Okay, so that's a good question. So you're in terms of talking about the rate laws, we'll get to that more. But this isn't a rate law. This is how we relate how much we make or how much we use of each of these based on the other ones. So this is stoichiometry, but stoichiometry with rates.
Oh,
Does that help?
yeah.
Okay. But we can get a rate of something versus something else. We're relating the rates of all the things.
Got it. Okay.
Okay. Why don't you guys go ahead and try to do water? Or not water, do the oxygen one. So there's your problem. I'll give you 2 minutes to work on that. Same process. Let's see, that's a oxygen, right? Oxygen's a reactant, so you might need to do something different with the sign.
Oh. Yeah. Yes. Yes.
Call me over if you have questions. We can rate of the CO2, so we can rate the CO2. We can also come down to water. So water is the it doesn't. Yes.
You can ask. I was gonna ask when I hear my answer. You just pick one up. Just pick it. We did it first. Yeah.
apologize.
But I think that it just needs to be up.
Honestly,
Yeah. So.
I'm here.
Okay, so let's go ahead and look at this one. So people were asking me, can I do water or can I do anything, right, for the comparison? You can do anything for which you have the rate, all right? So we had water, we had CO2. I'm just going to use CO2 since it's given in the problem. In case I made a mistake on water, that would help me, that would avoid me having problems down the line. So I'm going to remember that that's 0.020 for that. Actually, I'll do it over here in the corner. So I've got my equation for CO2 is going to be CO2 like that. It's going to be 2 because that's my coefficient in front. And then for oxygen, it's going to be, I have a 5 in front of the oxygen. Okay, and then I forgot one thing in terms of this equation. What did I forget? It has to be negative, right? Because oxygen's being consumed. Okay, and so what we've got then is I'm going to go ahead and if I go to solve this, these times are the same, so they're going to go away, and so I'm going to have 0.120 molar over 2 is equal to negative, whatever my change in oxygen concentration is over time. Well, we've got time, rate and the time there, or time and the rate. And so then I've got a negative and a 5. So are people okay with -5 like that? And then -5 over here. So that negative goes with the negative and the 5 goes with the 5. I can put that into my calculator. Clearly didn't get enough sleep because I don't remember the answer from last hour. 0.3. Okay. And so what I get is 0.30. I've got 3 significant figures, so I'm going to keep them going around. Molar per second is equal to my change in O2 concentration. I'm going to put that time back there because it is a change in rate. Okay, yeah.
Shouldn't it be negative because you're decreasing?
It should be. I forgot my negative sign. Thank you. Okay, questions? All right. Then we're going to go on and we're going to start talking about rate laws. So up there we were relating rates. If we knew the rate of one, we were going to figure out the rate of the other. But now we want to think about how we can figure out the rate of reaction based on the concentrations of reactants we have. So this is called rate law. This is rate laws. And in general, let's say I have a reaction that goes A to B. Okay. This is a simple reaction. We will get to more complicated reactions, but for now, I can describe the rate of that reaction, okay? So the rate of that reaction by a rate constant, okay, which is a constant specific to this reaction, and it's also specific to temperature. All right, a rate constant times the concentration of A. All that matters for a reaction rate is the reactants, not the products, and A would be raised to some power, n, okay, not an h. All right, and so for that reaction, depending on what that n is, I'll get different behaviors in terms of how this reaction rate varies with concentration. And that's shown with these pictures here. So we can talk about having, we're going to talk about having 3 different options here. Okay, we can have a 0 order reaction where actually the rate is just constant. It doesn't matter how much A I have around. I make the same amount of B. Okay, in that case, we're not dependent on A, and so that exponent n would be 0. Does that make sense? Okay, so anything to the 0 is 1, and so then the rate is just equal to K. First order reaction, actually A does matter. And so if I have more A, I will get more B in this case, or I'll get B faster in terms of the rate. And so we have this reaction here where if we double the amount of A, we get double the rate out. Okay, that's a first order reaction. It's first order in A. All right. And a second order reaction, what we have is two A's have to actually come together and bump together to or collide to get me to have a reaction. All right. And so this is the relationship we get, and the rate law looks like the rate's equal to K times A squared. Does that make sense in terms of that? Okay, so this you can imagine A just breaks apart, where A turns into something else. And then here, I'm going to have to come up with an example of a zero order reaction. They do happen, but I don't have one off the top of my head. Okay. All right, so those are the orders of reaction. That order of reaction, the exponent is really important. And it tells us something about how the mechanism, how do these molecules react to give us the products. And chemists are very interested in these sorts of things. Okay, there's also, so we can talk about the order of specific reactants. We can also have reactions where we have more than one thing involved in that rate law. So let's say we had A plus B goes to C, okay? The rate would be equal to, let's say the rate, well, I've got to put my rate constant, some constant K, some constant, it's a lowercase k, is equal to A to the, let's say, I'm going to just make this up, 3 A's and, or 2 A's, 3 B's. That's not to say we have 5 things that have to run into each other at the same time. Imagine how improbable that is, right? Up here, let's actually break out of this real quick and come back. Actually, let's finish this and then we'll go back. So if we think about this, what we do is we say the order of A is 2. That's what the exponent is, right? What's the order of B? Yep. Order of B is 3 because that's what the exponent is. The overall order is what is the sum of the two exponents. So what is the overall order? Yes. That makes sense? Just in terms of thinking about that. Let's go back here. So these things can be complicated, and we'll see more about that later. For today, we're not worrying about it. But let's talk about, so we're concerned with zero order, okay, great, first order, and second order. Second order is where we have 2 things run into each other, right? 2 A's have to run into each other to make this reaction happen. How many people play a ball sport? Okay? You get one of your teammates and you're both trying to make the ball, you both have a ball and you're both trying to make them hit, whatever device you use to throw the ball, hit the ball or whatever. How likely is that? You're trying to make them hit. You guys are pretty skilled, right? You could probably get them to hit, right, after a little bit of practice, okay? 2 things running into each other. Grab a third term teammate. Now, what are the odds of getting 3 balls to hit all at the same time? Okay, a lot harder, right? Okay, very unlikely that you're going to have 3 things in solution or in a gas all hit at the same time. So we don't have a third order reaction up here. Okay, this example down here is more for, this example down here is more for illustrating the concept. But really, you're not going to have 3 things hit each other at the same time. And so you're not going to see much in the way of ever having something third order. Does that make sense? Okay. So let's go ahead and think about an equation here. So we can determine one thing that's important is knowing this rate order is important, right? If I know something is second order in A, 2 A's have to run into each other. That's important for me to know as a chemist, okay? So being able to determine the rate order is important, and we can determine the rate order by changing concentrations of things. All right, so we're going to use this as an example. I pulled this one out of your book. I maybe should have pulled a different one because what is this? This is, I don't know the name of this thing. We're going to call this A, this complicated thing. It's a phenyl group. I can picture what the structure looks like, but I don't know the name. We're going to call it A. A is reacting with bromine to make a product, okay? So how would the rate change if A was doubled? All right, based on, here's my rate law, it's K times A to the what power? 1, okay? So A to the 1 and bromine to the 2. Bromine's being held constant, A is being doubled here. If I double the amount of A, if this goes up, if I double that, what happens to that? It doubles, right? If everything else is constant, the K is constant, the bromine's held constant. If I go from 1 to 2 here, I've doubled the value on this side, so I have to double the value on that side. Does that make sense? Okay, so that's great. We can actually express that with an equation. You can also do it in your head. All right, but these sorts of things, we expect that you're going to be able to do those sorts of conversions or calculations in your head. So the way I would express this as an equation is I would say the rate under one set of conditions is equal to the rate under a second set of conditions. Actually, I'm going to make this match the way I did it last hour. We'll put the first one on the bottom. It doesn't have to be that way. All right, I'm just trying to be consistent. Okay, that's going to be equal to the concentration. In this case, I'm going to I'll use A because I'm doing A, but concentration of A under the same set of conditions, right? The conditions is the concentration of A. Concentration of A there times an exponent. That exponent is the exponent that goes here, so that's a 1. All right, so the rate the rate 1 it goes with the A concentration 1. The rate 2 goes to the concentration 2, and that's the expression there. And so if I was to go ahead and put some numbers in here, right, it's saying double, but so I get to pick whatever I want. So I like 1s. So what I'm going to do is say, all right, so what happens if A is doubled? Well, A starts at 1. Whoops, I just solved it. I'm solving for X here. All right, so my rate is 1 when A is 1, right? If I double A, it becomes 2. And I know from my rate law that my exponent is 1. So 2 over 1 is 2, right? To the 1 is 2 is equal to X over 1 is equal to X. So X, if I double A, I double my rate. Does that make sense? How you would use the equation there? Okay. It's possibly more abstract than you might just want to do it in your head. All right. How would the rate change, given that we know that now? Just mess that all up. I'll let you work this and maybe I'll fix that. All right, we've got this reaction. How would the rate change if the bromine was doubled? Okay, bromine has what exponent? 2. So go ahead and either take a couple minutes, do that in your head, or use the equation and solve for that. What happens if I double the amount of bromine?
So we're doubling the rate for this one. Oh yeah, I'm sorry. I was asking about the one. I was still confused. So we're doubling this rate. So
You don't know the rate, you're over the concentration. And it's asking what's the rate. So this is actually the new rate, even right there, J2. That 1 is rate 1. That 1 is the concentration. We're just making up numbers that are easy because it's not giving us concentrations. We're about to do one where it will do that.
Yeah. Because it's only one piece that we, is that right, to one?
We are making up numbers, so we're saying that this could be a 4. And this could be, these numbers could be anything, as long as that new concentration double the old concentration. So that could be 16, that could be 1.
Oh, okay.
That could be 32, so then we go to 64 out there. We're trying to, we're using the equations, but we can make up our concentration, that's our starting concentration.
So you start.
Oh. Is that sort of?
Yeah, and I think the next one.
That's what I was looking
Thank you.
Okay, let's go ahead and do this one. So I'm going to do it using the equation. Can anybody, but I could also, when I was in college, I would do these in my head, right? So I'm going to, if everything else is held constant and I double this, and then I square the doubled, you get 4, right? So it's going to quadruple. Okay, but let's prove that using the equation. So we'll come down here. This is going to be for B. We're going to do our rate. I'm going to just keep the equation up there. It's got an A in it, but you know, who cares, right? We're just going to substitute with bromine. Actually, no, let me write it out. It'll be a little bit. So I'm going to write it out in the general form, rate 1 over rate 2. What we're doing is we have a bromine concentration that is our condition 2, right? That goes with rate 2. We've got a bromine concentration that is condition 1 that goes with rate 1. And then that's to the 2 because the power to the 2 because we have bromine raised to 2 in the rate law. Everybody with me? Okay. All right, so then I'm going to just put things in. I'm actually going to, if I don't use the ones, is it going to be, I was trying to show you can use any numbers you want, but maybe it'll be confusing if I don't use the ones. Anybody have an opinion? Okay. I'm gonna go ahead and just use the ones then. So what I've got is I've got my initial rate, I'm going to call 1. Okay. I've got some rate I'm trying to solve for. I go over here. I'm going to call my initial bromine concentration 1. I'm doubling the bromine, so I want to see what happens. 2. 1 over 2 is 2, squared is 4, right? 2 squared equals 4. X over 1 is x. So if I bring the 2 down to here together, the 2 ends together, I get x equals 4, or it quadruples. Does that make sense? Okay. All right. All right, then I've got another problem we're going to work here, where we're going to use the rate laws and we're going to use this equation again, but we're going to solve for a bunch more stuff. All right, so I might be interested. This has a rate law here, right? So I've got a reaction. It has 2 bromines over here. It goes there to there. What is that? What is that rate law going to look like? Just think about it for 30 seconds. You don't know everything about it, but what do you know about that rate law?
It's the same for bromine and oxygen.
We know that we've got the products, right? So do the products show up in the rate law? I'm making a face like they don't, but they don't. Okay, so if I was to write the rate law for this based on the information I have on the top, not having solved for it, I know that my rate is equal to some constant k, right? That I'm going to try to solve for this problem, times the concentration of bromine oxide, okay, to some power. I don't know what that power is yet. All right, I can't pull the power out of the equation like it's drawn. All right, we're going to get to something called rate limiting steps, and then we will be able to. But right now we can't. This is an overall reaction. We don't know what the rate is or how this reaction occurs. Does that make sense what I just did there? Okay. So now I need to figure that out. That's what it says. Determine the rate law for the reaction and calculate K. Well, I'm given two rates, and I'm given two concentrations. So if we look at remember our equation, there are 5 things in that equation. I'm given 4 things here, so I can solve for the 5th. All right, so here what it would be is I'd have my rate. I'm going to call my rate 2 over my rate 1. And that's going to be equal to my my concentration of bromine oxide, right? 2 over my concentration of bromine oxide 1 to some power n. And I'm given a rate. I'm given a rate and a concentration, another rate and a concentration, so I can solve for n. All right, so let's go ahead and do that. So I'm going to take my rate 1 here, and I'm just going to put it down in the rate 1. So I'm going to have 2.20 times 10 to the negative 2 molar over my rate 2 is 3.50 times 10 to the negative 2 molar. That's equal to my rate 1 is 1.43 times 10 to the 5th molar per second over my other rate is 3.61 times 10 to the 5th molar per second, and all that is to n. I need to solve for n. All right, so let's go ahead and do this. So 3.5, actually my exponents are the same, so I'm just going to take 3.5 divided by 2.2. And I get 1.59. Let's see, they've given me 3 sig figs, so I'm going to carry at least 3 sig figs along here. 1.59. Okay, is my ratio here? Actually, there's nothing else there. My units go away. And then on the other side, I'm going to divide that. I've got 3.61 divided by 1.43. And I get 2.52 to the n. So what power do I need to take that to? What power do I need to take 2.52 to make it 1.59? Okay, and it looks like it's going to be something smaller than 1, right? Because if I took it to 1, it would be something else. So now we're actually going to get a fractional power. That's weird. Okay, but let's see. I'm trying to think of how I solve this besides just putting things in until I get something that works. Anybody know the algebra trick here? By 2.52? No, I can't do that. Because the 2.52 is raised to this thing. What was that? Well, I can't square root it because I don't know it's not a 2, right? I'm going to put some things in my calculator. I bet you there's a trick here, and it may come to me as I'm doing this. And but so if I take, there must be like you've got a x to the y, right, on your calculator. Does it have an inverse of that somehow?
Yeah.
There is an inverse x to the y.
Oh, sorry. I'm trying to figure it out.
It's 0.5.
It's 0.5.
Yeah.
I'm not shocked, but it is. So So you guys are getting 0.5. Did you do that with your calculator with inverse x to y, or did you just do it putting numbers in? Okay, we're going to put numbers in for now, and I'm going to figure out how this x to the y key works. But I've got a y to the x here, right? So yeah, I'll get back to you on the algebra step here. I should know this, and I just don't. 2.52, if you put that in and you do an x to the y to the 0.5, you get 1.59. Okay. So this is going to be, this n equals 1/2, and that can happen. Okay, we have the 0, the 1, that's weird. Okay, but that can happen. We'll talk more later about how that sort of thing happens. But so now I know my rate law is this. My rate, right, is equal to K times my concentration of bromine oxide, okay, to the 1/2. And now I know from the data they've given me, I've got one of these and I've got one of these, so I can solve for the K, right? So now we're going to go back. We're going to go, actually, we don't even need to go back to the top. This goes with this, right? Okay, and the other one. Doesn't matter which one I use. So I can say my rate is 3.61 times 10 to the 5th molar per second, and that's equal to K times my bromine oxide concentration, which was 3.50 times 10 to the negative 2 molar, okay? And that's the 1/2. And so I can put in, I'm going to go ahead and I'm going to square that 3.5. So 3.50 e2 negative, and I'm going to go ahead and I'm going to take the square root of that. And so I've got over here, I've got 0.1870 is equal to 3.61 times 10 to the 5th. I took the square root of that, so I'm actually going to have molar to the 1/2. Okay, and over here I'm going to have molar per second. I'm going to have a weird rate constant. All right, but so now I can divide both sides by the 0.1870 molar to the 1/2. And so I got 3.61 e5 divided by 0.1870. And I get out of that K. So I've got half of this goes away, so this becomes a molar to the 1/2. My K is going to be 1.93, 6 times 10 to the 6th molar to the 1/2 over seconds. Okay? Weird number, but that's it. We solved for K. We solved for, that's our order of reaction. So we were 1/2 order in BRO, and this is what our rate constant is. Okay? Got our whole rate law based on that. Questions? Okay. I'm going to leave you there with that, and I will figure out how to solve more directly with your calculator for our next lecture.